So I'm going to be talking about reinforcement learning, which I think most of you are now little experts on, especially given your hard work over the past weeks on the workshop challenge that we've distributed. So my idea with this presentation today is basically to more or less review the theory in order that so that we all have a better informed discussion on Wednesday when we go into the practical details of the problem you had to solve. Okay? So you notice that I put the adjective advanced to this presentation. With that I mean that I'm going to try to give you a hint or a flair of the latest developments in reinforcement learning, in general reinforcement learning, not just for communications. But at the same time I also need to define notation, so I'm going to for sure be having some introductory slides at the beginning so that we all are on the same page regarding to this. So as I said, there will be some notation section of this presentation, and then I'm going to talk about the two main classes of reinforcement learning algorithms. That's polysyllabic grading methods and value methods. And then we'll go to more advanced stuff like deep reinforcement learning, multi-agent. And then at the end I have a practical example where I will show you how all of these theoretical algorithms can be put together in order to solve a real-world problem. Okay. So I'm sure everybody has seen this many times, but still, I can't emphasize it enough. This is what summarizes in pictures the definition of reinforcement learning, which a definition I like is that reinforcement learning means learning what to do, which mathematically sort of means how do we map situations to actions, okay? What do we need to do, or what is the best thing to do given the circumstances? And we model this with an agent. This is what we want to do, right? We want to write some sort of software, some agent, an intelligent agent that takes decisions given on the circumstances. And this is illustrated by the agent environment interface, okay? This is what we want to build, to think for us, to take decisions for us. And the environment is the surroundings of this agent. So the agent takes decisions by taking actions that have an effect on its environment. And how does this agent choose which actions to take? Well, the easiest way to respond to this question is to say that it just tries, okay? It tries actions randomly to see which ones work better for itself. And we model this by two outputs from this environment. Every time that the agent takes an action on the environment returns some information back to the agent, which means a new circumstance, a new situation, which we summarize by the state, and another signal, which is called the reward, that tells the agent whether that action was good or bad for the agent at any given point in time. So basically the agent takes actions sequentially, continuously over this environment, and its objective is to take the right actions. And by the right actions, I mean the actions that yield the highest reward. So that's what we have defined here, this magnitude, which is called the return. And the return is nothing more than the addition of the rewards collected over a long period of time. All right? And you see that this sum, this addition, is weighted by this other factor, which is called the discount factor. This is just to illustrate the fact that the value of the rewards decay over time. So yes, we want rewards, but we want them as soon as possible. And this is very easy to understand in terms of money. So if you have an agent that, I don't know, gets an euro when it takes the right action, the value of the euro decays over time. So a euro today is worth more than a euro tomorrow, and certainly more than a euro 1 year from today. So that's why we have this discount factor. Now, this discounting is not applicable to every problem, but it's certainly applicable in some of them. So it's an interesting generalization of this formulation. Okay, so how do we model the circumstances of the agent? We modeled it what we call the state. Okay, so I'm going to make a very simplistic picture. I hope you'll bother me for the simplicity, but I think it's very illustrative. So this is the classical grid world scenario, okay, where you have an agent which moves through a grid, okay? So the state can be justified by the coordinates of the agent at any given point in time. This would be, for instance, the state of the agent. So the agent will use this information to take its decisions. All right. So this state defines the state space for the agent. Another example of a state, taking an example from telecommunications, would be as follows. Maybe I can draw it here. Imagine that you have a base station and one UE. And there's another base station here. And this UE is connected to this base station. And this base station wants to take a decision, very simple decision, whether to hand over this UE or not. So you could very easily define the state for the agent running on the base station in terms of two very well-known magnitudes, RSRP and RSRQ. And this would be the state of this agent. Okay. Then a very simple algorithm would be basically just using some binary classifier, for instance. Whenever you have states in this region, you trigger a handover. Here, you don't trigger the handover. Okay. So this is just two simple examples of what you could describe with the state of the environment. Sorry, yeah. RSIP, reference signal received power, that's pretty much a measurement of the power that the UE receives from its base station, and this is the reference signal received quality, which is pretty much a proxy for the SINR on the downlink. I'm not sure if anyone wants a further explanation. That's just two simple examples of how you can define the state for the agent. And now you can make things more complicated. Once you get this output of the state from the environment, you could use it to construct more complicated features. You can do feature engineering. You can use some polynomial-based feature construction. And we call this X a feature vector. So S is the state as it's returned by the environment. And X is sort of an elaboration. It's another representation of the state that adds a bit more complicated features depending on the project you want to work on. This might be useful or not. And you can make this as complicated as you want. And probably the most generic way of working with the state is using artificial neural networks, which sort of build these feature vectors for you internally in the first layers. OK, so I continue with my notation description. Now I want to talk about the time dynamics. This is just a convention, but what I'm doing is here I'm using the subindex T to define the source state and the action taking on that state, but then I'm using the index T+1 to refer to the reward obtained in this transition. Okay? So here I'm representing two states. We can say that the agent finds itself initially in state 0. It takes an action, it gets a reward, and then it lands on another state. And this goes on forever, right? So in the simplest example, the agent would be here. It will take a decision. It will have a decision space, which we could define like this, for instance. Okay, so these are the 4 possible actions that the agent could take. The agent is here in this state, which has some x, y coordinates. It takes decision down. It moves here. Now it's in a different state. In this transition, we can get a reward, right? So this is just a definition of how the time dynamics is defined. Now, how does the agent decide which action to choose from the state, given the state it's on? Well, it follows a policy. A policy is another function that just maps the state to the actions, okay? And given a policy, we can define this other magnitude, which is important, which is called the value function. The value function is nothing more than the expectation over the return, which I defined in the previous slide. You can think of the reward as sort of the immediate pleasure the agent gets on a transition, and then you can think of the value sort of as the long-term desirability of a state. Okay, so maybe it turns out that this state has a very low reward, low immediate reward, but it gives you a very long-term high value. So the objective of the agent, what the agent should do, is to find a good policy, and a good policy is one that lands the agent in a state that has a very high value. It doesn't really matter if the immediate reward is very low. What matters is that long-term it gets as much reward as possible. And this is what's captured by this value definition. in a way, it's like, one example I like is, it's like deciding, I don't know, whether to study a career or not. So you decide you want to make a 5 years study, a master, and the reward is very low because you are very miserable and work a lot in the first years, but longer term, well, it should open you the door for better career moves, a better life, and so on. So it's important also to notice that the actions that the agent takes have an effect not only on the immediate reward it gets, but also on the states it can reach. So if the wrong action is chosen, this might lock access to states with higher values. So that's why the agent should not be myopic. The agent should not just focus on the immediate reward it's going to take. And in the same way that we have defined the value function for a state, we can also define the so-called action value function, which is pretty much the same thing. It's still the expectation over the return, but for a given action on a given state. All right, so these are two important concepts in reinforcement learning: value function, action value function. And these value functions are important because they define a cardinality in the policies. Now that we know that for a given policy we can calculate these values, we can also compare policies. If we have two policies, let's say pi and pi prime, we can say that policy pi is better than policy pi prime only if the value in all of the states over policy pi is larger than the value of all states for policy pi prime, right? So this gives us a very easy way or straightforward way of comparing policies. And since we can now compare policies, we know that there has to be an optimal policy. And by optimal policy, we mean the policy that has the highest value over all of the states. Okay, so I think these definitions are known to everybody at this stage. No questions so far, right? Good. So we get now to Bellman's principle of optimality, which basically is a fancy way of saying that we can always write the value of a state as a function of the value on the subsequent states the agent is going to get at. Okay? And this already gives you a hint of how to implement these sort of algorithms. I mean, we can find, if we can write the value of a state as a function of the subsequent states, this means there's some sort of recursiveness inbuilt into this algorithm. So we can use dynamic programming techniques to build this. A good exercise, I wrote here, by the way, just the Bellman equation for the value function, but you could as well write the Bellman equation for the action value function. That would be a nice exercise to do. Okay, so now we get to the two main categories of reinforcement learning algorithms. On the one hand, we have these policy methods. On the one hand, we have value methods. So policy methods, which are, I think, the most straightforward ones, are methods that will help us find an objective policy, in particular, an optimal policy. Because the policy what we ultimately care about, right? We want the agent to be able to take the right decisions on a given state. And that's given by the policy, right? You enter the state in your policy, which can be parameterized. This is just the parameters of the policy. And it will tell you which action to take, okay? We can formulate these policies deterministically, meaning that the output of this function will be just the action directly that we need to take. Or we can have also stochastic policies, which would map states to action probabilities. That would be a way of formulating a policy. And then on the other hand, we have value methods. Value methods do not try to learn the policy. They try to learn the value function. And very often, they try to learn the action value function. Why? I mean, if what we ultimately care about is how to behave, why do we care about the action value function? Well, if we know the action value function, we also know the optimal policy. I mean, as long as we can calculate how good each action is, the optimal policy is just choosing the action with the highest value. So it's pretty straightforward to get the policy from the action value function. And value methods have an advantage is that they converge a lot faster usually than policy methods, but they don't have convergence guarantees. So depending on the problem you're trying to solve, you might want to try one or the other. other advantage about policy methods is that they are a lot more scalable, because as I said before, the output of this function can be the action directly. So if you have a huge action space with millions of actions, or even just a continuous action space, you might want to try policy methods, because you can get the real number action right at the output of this function, but you cannot do that with Q functions. Also, modeling of stochastic policies is straightforward with policy methods, because as I said, you can map here the state to action probabilities. And on the other hand, yeah, these things take like forever to converge. So it's good to know the pros and cons of each. Depending on the problem you want to solve, you might want to look at one or the other.
So on the one hand, we get less convergent guarantees, and on the other hand, we converge to local optimum. So which one is worse?
Yeah, that's a good point. I'm just listing the pros and cons.
Okay, but in the value methods, you don't even have guarantee of any type of conversion. So
but I think that in some cases, for example, when the action space is continuous, even if you have the optimal value function, the state value function, you cannot. It's not easy to access to get those things.
If you have a continuous action space, you will most likely be working with policy methods. I haven't seen any work with continuous action spaces with.
You start, and it's not easy to get to 5 star. So in some cases, the problem is the first one.
what are the convergent guarantees we have?
Well, this is just a category of methods. I'm not speaking about any method concretely. So each method has its own proofs and its own warranties. But
for value mapping, for tabular Q-learning, we have
yes.
Yes.
Yeah, Q-learning is, I mean, that's why Q-learning is probably the most successful reinforcement learning algorithm today. Because, as you said, there are warranties, and it works very well in practice, and now we have DQN, so it works pretty much well. You do not, we do not, but it works well in most of the applicable cases. Yeah. But again, these are just categories of methods. I'm not talking here about any method in particular. So any claim here is generic. Of course, you will have to look at the particularities. Again, one thing I didn't highlight, as I said, that one thing I like about value methods is that you have here in-built quantification of the expected return, which means that sometimes you don't really care about the optimal behavior, which is what you get with the policy methods. Sometimes you really care about the value of the actions you're going to take, because and this is what gives you here. It gives you an estimation of how good the actions are going to be, and sometimes it's enough. Maybe even if you knew what the optimal behavior would be, with this method you wouldn't necessarily know how good they were. So maybe it turns out that the best the best action to take is still pretty bad for your intentions. That's why with value methods you get this quantification of how good an action is going to be, and then you can decide whether to ignore it or maybe explore or do something else. Okay, so now I'm going to review again very old reinforcement learning methods, but these are important because they settle the basis for the ones I'm going to explain about later. Okay, so reinforce. This is the one of the, sort of the ground algorithm, the ground policy-based method for reinforcement learning, and it's pretty straightforward. Basically, what you do is just look at this line here. You just begin with some random policy that you can randomly initialize, and then you use this policy, you follow this policy, and you capture what we call a trajectory. Okay, a full episode, which means that your agent begins in some state, and then it uses this policy to take an action, get a reward, and reach a new state. And you do this for as many times as you want, or until the episode ends. Now, up until this point, we haven't trained anything, but after this finishes, then you go back and replay every single step of this episode, and on each of these states to calculate the return. Now, the return is, as I said before, the addition of the reward from the state you're in until the end of the episode. So you can calculate this easily in each time step. And then you take this return and use it to update your parameters. These are the parameters of your policy function. Yeah, I'm not going to prove to you, how this equation comes about, but there's a theorem called the policy gradient theorem that explains this for you, improves this for you. Basically, what's interesting to me is that this logarithm comes from the fact that the grading of the logarithm equals the grading of the policy divided by the policy itself. So that's pretty much where this logarithm comes from. And you do this many times. You can do this several episodes until it converges. And this is how reinforce works. It's important to highlight that the policy must be a differentiable function. Otherwise, you couldn't do this. Now, this is the example that Richard Sutton gives in his book for reinforce. I don't like it very much, but it seems to be ubiquitous, so I thought I'd bring it up. Basically, he calls this the short corridor environment. Okay, so this is a pretty easy environment. It's an environment with only 4 states. Okay, 0, 1, 2, and 3. And the agent begins in this state, and it gets a reward of 0 on every time step, and a reward of +1 when it reaches this state. Okay, and there are only 2 actions, right and left. And those actions, they have the usual meanings, except on this state, where the actions change their meaning. So basically, if here you take the action right, you end up back at the start. All right? And in this environment, all of these states seem the same to the agent. All right? So there's, you could say that the agent pretty much has no state information available. So since all of the states seem the same to the agent, you cannot do a deterministic policy here. You have to have some sort of a stochastic policy where you just choose right or left with certain probability. And you can apply the reinforced algorithm here just to find out what the probability is for each of those actions. And this is pretty much the performance of reinforce. You see here that all the information the agent has is these actions he has taken, but it really doesn't know in which state it's on. I think, in my opinion, that maybe a better name for this environment than short corridor would be the dark corridor, because it's like the environment doesn't really know in which part of the corridor it's on. And reinforce provides pretty good performance. It just requires some fine-tuning of the learning rate. Okay, so that was a policy method. Now I'm going to show you the other, again, very old main value method, which is Q-learning, which we just discussed. So Q-learning is a control algorithm, which contrasts with prediction algorithm. Basically, control problems are problems where you want to find the optimal policy. And then you have other type of problems, which are called prediction problems, where you're giving the policy, but you want to know how much value you get on each state. One advantage of Q-learning is that it's of policy, which means that even if you don't know the optimal policy at the outset, you can still follow any random policy if you want to explore the environment, and in this way reach convergence on the optimal policy. And in Q-learning, basically what we do is we store a huge table in memory where for each of these states and each of the possible actions, we store the action value function. And we apply this equation update repeatedly, and we update this table on each update. And you see here that to update this table, we're updating the table using a learning rate, which basically scales the error that we're making in the prediction. Okay, so this is the value, the original estimate, and this term here is the error that we had on this estimate for a given transition.
Excuse me.
Yep.
At our policy point, you said that Q-learning, even if it doesn't know the policy, it can still follow the policy.
No, sorry, yes. Originally, you don't know the optimal policy, right? Because you can initialize this randomly or to zeros or to something. So at the beginning, you have no idea what the policy is. But since you don't know it, you cannot follow the optimal policy. But you will eventually find it. It will eventually converge to the optimal policy, even if you're following some random policy in your behavior. Because every time you make a transition, you're updating one of the cells on this table.
But we still get the policy at the end, right?
Yes, this is guaranteed to converge. Yeah. It still requires some calibration, especially regarding of the learning rate, but it's guaranteed to converge. Yeah.
Another question: how do you, when I have a Q function, I think there could define many different policies based on this Q function, right? Doesn't
Yes.
There needs to be any kind of stochastic policy on top of this. Or
Yes. Yes. You don't even need a Q table to have a policy.
but how? So is there now? So there isn't a one-to-one mapping now between Q function and the stochastic policy, or is there?
Okay. If you had the optimal Q table, the optimal Q function, then you would also know the optimal policy.
Would it be a deterministic policy? Would it be stochastic?
It would be a deterministic policy.
Deterministic.
Yes. Yes.
There's no randomness here, right?
Well, you can behave randomly for exploring. You don't need to follow the optimal policy even if you know it. Sorry?
After training, I mean. When you have the optimal actually Q table,
Yes.
there's no...
Yeah. If you have the optimal Q table, you also have the optimal policy, so what's the point of doing something different? There's a point of, having random behavior during learning, trying different things, see if some work. But, yeah.
Okay, but then for the problem, you reinforce this corridor thing.
Yes.
Where stochastic policy seems to be optimal, you couldn't learn against this thing.
That's the thing. And the other problem, you didn't have a state. So you wouldn't have a table. I mean, that problem is very easily solved if you do have a state. If you number those cells I showed, 0, 1, 2, 3, and 4, and you give this information to the agent, then you can do deterministic policy. All you need to do is to be aware that on the second cell, the actions reverse meaning. But I think that's why I don't like the example. I mean, Richard Sutton chose this example to highlight the advantages of reinforce, but the problem can be solved via easier ways if you know information about the environment.
But does this mean that for every problem, the optimal solution is a deterministic policy?
No.
When you have a state, that's my question. So when you say
No.
it's the optimum Q table,
Yes.
and this results in the optimum deterministic policy, this means it can only be optimum for a problem for which a deterministic policy is optimal.
Yes. I don't know if you could have stochastic policies.
I don't know if my question makes
I-
sense.
I think that for all stationary environment, there is always an optimal deterministic policy. It's just that it's not necessarily the only one.
There is a condition that you have to have limited horizon in order to add deterministic optimal.
It could be. I think I have seen somewhere that you can map these Q values to probabilities as well, but I'm not sure exactly how you would do that. Maybe I don't know. Some softmax, I guess.
Actually, the learning demonstrations, they prove mathematically that if you go through every state in action a certain number of times, you actually converge the optimal policy always.
Yeah, but it's a deterministic policy.
Yeah.
Yeah. But again, I think I saw somewhere that you can actually map these Q tables to stochastic policy somehow, but I'm not very familiar with how you would do that. I don't know. Again, this is just a comparison somebody made between deep implementation of Q learning and reinforce for this particular Doom video game. You can see here that basically Q learning kicks ass, but just a short comparison. Okay, so enough for ancient history. Sorry to bore you with that. Now we begin with more up-to-date stuff. This is DQN, which again, I'm sure pretty everybody knows. DQN is nothing more than the deep learning version of Q learning. Okay, so what we're going to do is, instead of having a table, because there are some problems with state spaces so large or action spaces so large that you just cannot fit a table in memory. So for those, what we do is we have a function, in this case approximated by a neural network, that we use to approximate this table. Okay, so we have a neural network where we enter the state as it's delivered by the environment, and then we have as many output neurons as actions possible. Okay, so for a given state, we can automatically predict the Q value for that state. Now notice that this state is the pure state as delivered by the environment. So we are not making feature engineering here. We are not defining any new feature vector from this S. We don't need to do that because the neural network can be trained to do that for us. If there are, I don't know, quadratic features needed for this state, this will be computed a few layers within the neural network. Okay, so this is again the Bellman equation. So we know that the optimal action value function can be written in terms of the optimal action value function on the subsequent states. And this again means that we can actually use this right-hand side here to compute the targets to train our neural network. The insight of DQN is that even though it's a reinforcement learning method, we still need to train this neural network. So the way DQN does this is using supervised learning, which means that DQN uses a data set of samples and labels. And the samples we have, we can collect these samples from experience. But what are the labels? We don't have the labels. We don't know the cues initially because we're learning as we go. So the way DQN does this is by actually having two neural networks. One network is called the online network. The other one is the target network. The online network is the network that we're actually training very often. And the target network is the network that we're using to predict the labels of our training data set. And this basically means that when we run a training epoch, we update the online network, but we only update the target network every, say, 10 or every 100 training epochs of the online network. And this helps us keep the targets stable and avoids non-stationarity. Because if we were actually using the online network to predict the labels themselves, they would be changing too fast, and then the whole thing would just not converge. So Q-learning does this by defining this loss function, which is again nothing more than the targets from the Bellman equation and the current predictions done by the online network.
So in this loss function, which one is now computed by the target network?
Yes, this is highlighted here. You see that theta refers to the parameters of the network, and this one has a minus. Minus means that these are old parameters. So this is the target network. Old because you don't update this very often. So basically, you update this network. This is the online network. And every 100 training epochs, then you copy these parameters onto the other network, which you use to calculate the targets. Okay? And again, you need to do this for stability. Otherwise, the targets will be varying so widely that the thing will never converge. Okay, so this is called experience replay. It's also a main ingredient within DQN. How do we do that? How does it work? Now, the agent is taking decisions sequentially again. Okay, so what we do is we collect those transitions. So every time the agent is at some state, takes an action, gets a reward, and lands on a different state, we collect this as a tuple, and we store it in this memory. This is called the experience replay memory. Okay, and this can be very large. So it's actually the size of this memory. It's a hyperparameter of the algorithm. It's usually implemented as a FIFO or as a circular buffer, which means that when you fill it, the next transition that comes will overwrite the oldest transition. So basically, the size of this network is an important parameter for the algorithm. And now comes the question: how do we train? How do we get the training data to train our neural network with supervised learning? Well, we go to this memory. We train by batches. So we extract. Let's say that your batch size is 8. So we get eight transitions. We use the target network to compute the targets for those transitions, and then we use this batch plus the calculated labels to train the online network. Okay. So that's the idea behind experience replay. And the way we build the batches is by sampling at random from this memory. Okay. So this is important because if you see these transitions are stored sequentially, and one main requirement of stochastic gradient descent is that the samples that you use for SGT to converge need to be independent. And if you took 8 consecutive samples, you would be breaking this requirement for independence because there's a strong correlation between subsequent transitions. That's why it's important that your sample are random from this memory. Okay, now this is a small improvement over DQN that was made a few years later. which implied that instead of using fully connected networks, you'll be using this so-called dwelling architecture, which is a bit different. And instead of having fully connected network layers until the end, what you do is you separate earlier in the first layers the flow of your data into two separate streams. Okay, so now we have pretty much two neural networks with one common input layer, and they calculate two different things. The upper stream calculates the value function, and the lower stream calculates the advantage function, which is basically the difference between the action value function and the value. And this is interesting because it allows us to estimate the value of states independent of the advantage provided by each action. There are some states in an environment where the action you take doesn't really matter. So in those situations, you don't really need to know very precisely what the action value is for each action. So in that case, it's sufficient to know the value function. So these networks are a lot easier to train. They converge faster. And they had, back in 2015, they provide certainly advantages in performance over the standard DQN.
Why do we need this mean branch?
Sorry?
It's this mean.
Yeah, this is just to normalize. You just compute the mean over all of the advantages, and then you subtract it. Such that the mean is 0 here. This is for stability reasons. It plays really no major role. I mean,
and you train this only on Q. I mean, when you train this network, you have you train only based on the output Q of.
Yes. Yeah, this is still a Q network. The whole thing, that's the output. It's still a Q network.
A very naive question. Once it's trained, how do you know that's what you got on the upper branch is V, and on the lower branch is the advantage?
You don't. You don't know this.
This is an interpretation of what the network is given.
Yes. Yeah. Yes. I guess you could have an insight, but in fact, I think that's. Have you read this paper? No. If there's there's a mention in this paper that if you don't do this subtraction, then the semantics are clear. Then you will get the value here and the advantage function here. When you do this, you don't have this meaning anymore. But and in fact, the authors actually try several implementations. So they say that they converge to doing this normalization for stability reasons, but I think there was another option where you could actually divide by the maximum advantage that you had. So they try several approaches here that sort of lose the semantics of the advantage function. Okay, another technique that was proposed in 2015 is the so-called double DQN. Now, one problem that DQN had is called over-optimism. Now, this is the same equation I showed you before that we use for the loss of DQN. And you see here that when we calculate the targets, we are always choosing the maximum action value prediction. Okay? And this, of course, adds too much optimism. We are not always going to have such high action values. That's why what double DQN proposes is instead of choosing always the action that yields the maximum action value, you use the online network, which is more up to date, to choose the action, and then you use that action to calculate the target over the target network. Okay. So you have two steps here. First, you have to choose the action over the online network, and then you use that action to compute your target. And this reduces over-optimism, and again provides high performance over the original DQN. Okay, 2016. 2016, somebody proposed prioritized experience replay. Now, you remember that I said at the beginning that we were sampling at random from the experience replay memory, but you don't necessarily need to do that. So the idea behind prioritized experience replay is that instead of choosing random transitions, we would only choose those transitions for training that are more interesting. What does interesting mean? Interesting means that, that the predictions were unexpected. And that's why, together with the transitions, we're also storing this vector, which is called the TD error, the time difference error, which we know because we are calculating that's this difference on every time step. So then, how do we sample from this memory now that we have the errors? Well, we just need to map these errors to priorities, and then we just choose, we do weighted sampling from this memory. And the authors of this paper propose 3 different methods to do this. The first one is greedy TD error, which means basically that we would choose the priorities with the highest error. Another approach to some sort of a stochastic sampling. Proportional means that we will map these errors to probabilities of being sampled, maybe using softmax. And then the third approach is called rank-based stochastic sampling, which basically means that we still store the errors, but then we assign a rank, which is basically a cardinality to each transition, and we use that cardinality, that rank, to compute the sampling probabilities. Okay. And this again provides many performance boosts. I think the main conclusion of this paper is that stochastic ranking provides the highest gains over the default DQN, which is right low here. I think this is this Atari testbed video game. Any questions so far? Okay, so now we get, I think 2016 was a very prolific year in terms of results for reinforcement learning, and this is A3C, which I know that many of you know from this workshop challenge that we organized. This is basically the deep learning version of reinforce, which was the algorithm I explained before. And the name is a bit of a tone breaker, asynchronous advantage actor critic. What does it mean? So asynchronous stands for multiple actor learner threads. So basically, with this algorithm, we will have many threads with many learners. Typically, you will have one thread per CPU. And what they do, each of these agents has its own copy of the environment, and they interact with the environment, collecting transitions, and they send these transitions to some centralized learner that gathers them all, makes the training, and then distributes copy of the network to the distributed learners.
Asynchronous because they don't need to have the same model at the same time.
Yes, among others, yes. Yeah. And you could have some even distributed in different machines. One would be on iteration, I don't know, 1,000, the other one only on iteration 10. Okay, it's a bit blurry, I think, because of the screen position, but basically this is the same algorithm as reinforce, okay? So basically what you do here is you have initially some randomly initialized neural network that you use to approximate your policy. And then you use this neural network to collect trajectories for one full episode. And then what you do is, again, you replay once again that episode, and then you use that replay to compute the return once again, just as we did in reinforce. So you use the same algorithm. And then you use this return to update with the weights of your neural network. Now you see that this neural network now has sort of 2 heads, which is similar to the Dueling network I showed before. Okay, so it has one head for the policy and then another one for the baseline, which is in this case an approximation to the value of the state. The value is only used to update the policy. And the authors actually of this paper showed performance results. I think this is very interesting for different number of threads: 1 thread, 2, 4, 8, 16. And you see that the more agents you add, which basically means that the more money you have to buy CPUs, well, the best performance you're going to get. And the explanation means that the explanation is basically because the more agents you have, the more successful your exploration of the environment is. So you get to collect more data. And if you join this with prioritized experience replay, it's even better because you can only choose the most interesting transitions from all of your workers. In my opinion, I think this is sort of an example of why most of the deep learning research today is made in companies and not in universities, because yeah, you need money to buy hardware. So yeah.
One question, sir.
Yeah.
But this slide, it works in the scenario that you can explore. It's kind of the game or something. You can produce data easily. But if you want to make it work for something actual, having many agents means, I mean, you need to sample your environment. So if you can simulate your environment inside the computer, it's easy to have several agents. But otherwise,
Yes. Well, I guess it depends on your problem. Hold on. Turn this off. Well, I said that you can have these threads running on CPUs, but you could think of, but not necessarily the case. I mean, this could be separate machines. Imagine that you're training, I don't know, you have some algorithm that runs on base stations. You can think of each of these threads as one base station, interacting with the network, with the surroundings, with its telephones, and collecting transitions, sending them to some learning server somewhere in the cloud, and then collecting the training networks from them. So this could be base stations or wherever you want to deploy your algorithm in the end. And that would not be a simulated environment. That would be a real environment that you were working on.
Now, when multiple base stations, they wouldn't see the same environment.
Yes, that's true.
So you require that these are clones of the same.
Yeah, that's a good point. Yeah, fair enough. Yeah. I cannot make promises on how that will work, I guess. I mean, there are some problems that are, even if they are spatially separated, they will have some similarities in terms of distribution and might work. I don't know. Handover decisions might be one. But if you're thinking more of physical channel estimation, well, that's a different story. Okay. So now we're going to talk about multi-agent reinforcement learning, which is like, the difficult version of reinforcement learning. So up until now, we're talking about single agents, one agent interacting with the environment. But there are some problems where you actually need more than one agent to working together to solve the solution. A typical example is a football team. That's just multiple players working separately, taking independent decisions. Again, if you have a network of base stations, one example I like is PCI selection. So imagine that you have base stations, so your Voronoi diagram would be something like this. I don't know. And imagine that you want to use reinforcement learning so that these base stations choose their own PCI. Okay, the PCI is the physical cell identity of the cells. That's how a telephone knows whether it's connected to this one or this one. Okay, so if it turns out the PCI for this cell is 1 and this one is 1, and you have a telephone here in the border, well, it would just be confused and would have no idea which cell it's connected to. So ideally, you want to have different cell IDs. And if you're using reinforcement learning to do this is again a multi-agent problem, because you have decisions being taken distributedly over space, and they all need to cooperate with each other somehow. So this is just one example of a multi-agent problem. On top of that, of the football team. So this is what multi-agent reinforcement learning looks like. Now we have still one environment, but we have many more agents. And those agents are also taking actions that have an effect on the environment. Now, the environment, all the actions of all of these agents are aggregated into this vector, which is called a joint action. And the environment only evolves after one joint action is exerted over this environment. And now there's a small difference. Now before, in the single agent case, the environment was delivering the state onto the agent. But now we don't use the letter S anymore, we use the letter O. to refer to the fact that these are observations that each agent has over the environment, okay? So, and these are different. I mean, this agent does not have access to the observations of the other agent. That's what we call this problem, this is a partially observable problem, okay? So it's usually modeled using a partially observable Markov decision process, or a POMDP. And this has some implications on the training algorithms that we're going to be using. So the agents also receive, on top of the observations, they receive a reward from the environment. If all agents receive the same reward, we say that this is a cooperative problem, but this doesn't need to be necessarily the case. Okay, it could be that some agents will get a higher reward, which means they will have an incentive to behave differently from the other agents and beat them somehow. So this model allows for both cooperative and competitive approaches. Now comes the question, how do we train these agents? Perhaps the most straightforward way of thinking about how to train them is just to take one of the algorithms I showed you before, like DQN, and you have multiple agents training in parallel. Okay, so you just take DQN and you train n times. This doesn't work.
But these agents work for a common goal?
They could, but they don't necessarily need to. So as I said, if you provide the same reward to them all, they certainly have the same common goal, because they all want to maximize the same return. But if you don't provide the same reward to them, it doesn't need to be cooperative. That doesn't mean it's competitive, but it doesn't need to be collaborative.
So somehow they don't know about each other at all? Like, then why can't we just use single agent?
That's a good point. Each agent sees the other agents as a part of the environment. So unless if you are explicit communication channels between them, which you could as well.
It's still a Markov decision process.
It's a PO Markov decision process. It's partially observable because not a single agent has access to all of the information. Now, well, in general, of course, there are multi-agent problems where all the agents get the same information. Think of chess. Chess, you have two agents, and they all see the board in full. So that's a case where it's not partially observable. But in the generic case, it's partially observable. Okay, so again, how do we train this? I mean, the easiest way is independent Q-learning. As I said, you have the QN on one agent, and you clone this agent, and they all train in parallel. Now, this is super easy to do. You just need to replicate your code. And as I said, each agent sees the other agents as part of the environment. But now it turns out that you have multiple agents training in parallel and changing their behavior because they are learning, they're exploring, they're finding their own policies. So the behavior is learning. And since all of the other agents are part of the environment from the viewpoint of another agent, this leads to non-stationarity. So the whole thing does not converge, at least not theoretically. There are no guarantees. But the fact is that there are many papers where this actually doesn't work that bad. The most remarkable paper about this is Pong. I think that was in 2017 that somebody actually did multi-agent DQN for Pong, and it works well, even though there are no theoretical guarantees for convergence. So I want to show you one example I like on how to do multi-agent reinforcement learning. Again, this is a very old example. It's called the Minimax Q-learning algorithm. And the problem where it's illustrated is this one. It's called Markov soccer. So the idea is that you have two agents. One of them is in possession of the ball. There's only 4 possible moves, up, down, right, and left. And whenever the agent with the ball steps into the square of the other agent, it loses possession of the ball. Okay? In this problem, now you have two agents that need to find their optimal policies to beat the other one. I mean, I think the reward on every time step is 0, and you get a reward of +1 when you make it to the ball to the other side of the field. Now, in this particular environment formulation, a deterministic policy for both agents never works, because it's always possible to block access to the goal to the one in possession of the ball. So the only way to beat this is with some sort of stochastic policy where you do unexpected moves to the sides that the other one is not expecting. So we need to find this optimal stochastic policy, okay? And the way Littman solved this back in the day was with this minimax algorithm, which I think is very intuitive as well. So basically we have this algorithm running in both agents, okay? So we're running in duplicate. I'm just showing it here for one agent. I'm showing it for agent A. And this is a tabular method. We still have a queue table that, as before, is conditioned on the current state, on the actions of the agent, and now it's also conditioned on the actions of the opponent. Okay, so it's a three-dimensional table in this case. And what you do is you initialize your policy randomly, or well, in this case, you just initialize it, all the actions to a common value, and then and you just follow this policy to collect transitions. And this is the update equation for the table, which again has some learning rate that is decayed over time. And this is where the minimax insight comes in. What we do is, how do we update the value of the state? By the way, the value is just used to update the queue later on. So if you ignore this max here and you just look at the min, this is basically the lowest action value we can have depending on the actions of the opponent. Basically, this is the value that we would receive if the opponent behaves in the way that makes me most miserable. Not sure if that's clear. That's why this min is here. That's the worst experience we can have if the opponent behaves optimally. And then what we do is we basically just maximize this magnitude over the policies to get this most miserable value as high as possible. And by doing so, the whole thing converges, and it has some advantages because it's shown to converge to the Nash equilibrium. It means that no agent could be better by choosing another policy. And and it certainly performs a lot better than independent queue learning. But again, this is a tabular approach, so not very scalable, especially for large field sizes.
Multi-agents always partially observable?
Sorry?
Multi-agents, multi-agent queue are...
Not in this case. In this case, the state, all agents have access to the coordinates of the opponent, whether they have the ball or not, so on. This is not partially observable.
So partially observable is a different problem.
Sorry?
Partially observable is not...
It doesn't apply to this problem. In this example, both agents have access to everything, to the same type of information. But in this case, they get different rewards. One agent wins means the other one loses. So this is clearly competitive. Okay, so this slide looks boring, but it's super important. I think it's a very good summary of what are the main pathologies of multi-agent reinforcement learning. What makes multi-agent reinforcement learning difficult as a problem? Well, the first problem is the moving target, non-stationarity, which I already mentioned. Okay, so we have multiple agents. They are all training in parallel. They're changing their behaviors, which means that the environment is really non-stationary from the viewpoint of a single agent. That's a challenge. Second challenge, the curse of dimensionality. I mean, single agent reinforcement learning was difficult. If you have 100 agents, well, it's even more difficult. You certainly need more computing power. You certainly need more memory. Partial observability. Well, now it turns out that the agents do not have access to everything that is known about the state of the environment. So the information they have is partial, is incomplete. How do you solve this? Well, usually you solve it with memory. So this problem of partial observability means that an agent may be on a state and take an action and land on a different state. But 10 milliseconds down the road, it's again on the same state, it takes the same action, but the result is completely different. And that's just because other agents that the agent cannot see have taken different decisions. Okay? So how do we disambiguate these transitions? This is usually done with memory, which means that you could have some memory-capable neural networks like LSTMs inbuilt in your agent. Or you could have some sort of representation of the states that collects all past agent-environment interactions that make a difference for the future. Usually you would collect all the transitions of the past and take decisions based not just on the current state, but on the past 100 or 1,000 states. Multi-agent crate assignment, that's another problem, another challenge within multi-agent, which means when we have multiple agents taking actions on the environment, how do we quantify the reward? How do we give credit to an agent and make it responsible for the responses of the actions? Surely some agents make some useless actions if they're in a collaborative setup. So this makes it very difficult to design reward functions. Right? Designing the reward function is one of the main challenges in reinforcement learning, and certainly even more difficult when you have multiple agents doing that.
This means you are sometimes not sure that your own, the action of one agent is responsible for reward or the behavior of the others.
In a collaborative, exactly. Okay. Not of the behavior of the others, but on the response of the environment. Imagine a collaborative setup, I don't know, a football team. One guy scores the goal, but how much credit does that guy get compared to the other ones? That's sort of the challenge. Global exploration. This basically means, global exploration means the probability that one agent is exploring. Now, if you have multiple agents learning, when one of those agents begins to behave randomly just to explore its action space, this may destabilize learning of other agents. So this, again, is a challenge. So you have, the way most papers have seen solve this is by introducing exploration schedules, which means that they prohibit that all agents explore at the same time. And then finally, you have relative overgeneralization, which basically means that multiple agents may get stuck in local optima rather than hitting for the high peaks. So these are sort of the main challenges that you will encounter in multi-agent reinforcement learning. Now, most of the works on multi-agent deep reinforcement learning fall into one of these 4 categories that I've drawn here. So I'm going to try more or less to summarize them all to you for you. The first one is emergent behavior. Basically, this category means you take the good old single-agent reinforcement learning algorithms, you clone the code on multiple agents, and you see what happens. Then you have studies on learning to communicate, which means now we add a communication channel between 2 agents and allow them to exchange messages and see if that helps in learning better policies. Then we have works on learning to cooperate, where you have many agents giving some sort of some task, and you take basically the old tabular methods from the 90s and try to apply them anew in deep reinforcement learning approaches. And then we have a category of study of works called agents modeling agents, where the idea is that one agent tries to model the policies being learned by the opponent in order to try to predict their strategies. So these are sort of the main categories of works in this area. This is just an example of emergent behavior. I think I mentioned this previously. This is just the Pong example. So somebody took DQN and applied it in 2 different agents, and it turns out they converge, even though this cannot be guaranteed theoretically. I think this paper tried 2 approaches, one competitive, one collaborative. The competitive setup means that if one agent wins, the other one loses. And the collaborative means that both of them lose if the ball gets out of the screen. And both reward schemes are shown to converge, at least in simulation. Okay, learning to cooperate. This is another interesting approach, which is called lenient multi-agent reinforcement learning, which revolves about 2 main ideas. The first one is called hysteretic Q-learning. Hysteretic Q-learning means that we just add a hysteresis on the learning rate. So we have actually 2 learning rates. And what we do is whenever we're going to update the network in a way that reduces the predictions, the Q predictions of the network, we use a very small learning rate. And if, on the other hand, the update is going to increase the prediction, then we use a higher learning rate, which in a way introduces, again, over-optimism, but it turns out it works pretty well. And the second idea around this paper is called leniency. I didn't understand this word in English very well, but it's sort of a synonym with mercy. The idea is as follows. As I said before, you have many agents. And for the viewpoint of an agent, this agent will find itself very often on a state and take an action on the state and receive a reward. And this will happen many times with the same state and the same action. So rather than training the network on each and all of those transitions, you only train it in the transitions that have the highest reward. And the reason why they call it leniency is because they assume that the transitions with low reward are due to poor decisions by part of the other agents. So it's sort of like a presidential pardon to those other agents for taking poor decisions that yielded a low reward. That's the main idea behind this lenient multi-agent reinforcement learning. Okay, this is my favorite topic, learning to communicate. Here what we do is now we have, again, multi-agent setup. And what we now do is that these agents can exchange messages between themselves. And they can exchange messages from a fixed size vocabulary with also limited size message length. And this is just one toy example that most people use. These are called speaker-listener games. In this particular game, we have a speaker that is shown some figure. And then the speaker has to describe this figure to the listener. This is another agent. And the listener has to reconstruct the original figure. And by reconstruct, I mean choosing properties from a very large property space. And both agents get a reward when the reconstruction of the listener matches the figure that was shown to the speaker. So how do we do that? Well, there are many proposals. This work by Foster is one of the most important papers on the area of learning to communicate. Basically what we do, we still have a queue network that receives observations from the environment, but now it has another input, which is the messages that it receives from the other agent. And not only that, there's another change. Now we have, we still have the same actions as before that have an effect on the environment, but now there's other set of actions which are called communication actions. And those are the messages that this agent is sending to the other agent. And again, this can be trained. This red arrow just shows the gradients. We can still use gradient descent to train this network. And you can train these systems in two ways. You can do independent queue learning, which again has its own stability challenges. So that means that both agents will be training the networks in parallel. But the advantage of this scheme is that you can collect the transitions and train them centrally in some sort of parameter sharing setup, and then copy those trained networks to both agents.
Sorry, I didn't really get the last part. So you centrally, so you don't have the partial observability constraint anymore in this centralized training, or do you?
In this example, the actions of this guy are the messages, and the action of this guy, they have different action space. That's on the first hand. But then the observations, they're different. This one does not have access to these observations. It only has access to the messages it receives. So yes, it's partially observable because they don't see.
I was referring to the last thing you said, that there is this parameter sharing.
Yes. How do you train? Because you have two agents, and each agent has its own queue network. So how do you train it? There are two ways to do this, and in fact, the paper covers both the scenarios. Option one is that you do independent queue learning, which means you train those queue networks on their own in parallel. Again, this has problems of non-stationarity. And the other option is that you have a centralized server that collects the transitions and does the training for you. So there are these two ways of training. And the paper shows that actually when you do centralized training, it converges faster, higher, and blah, blah, blah. And they don't do experience replay here, by the way. And apparently, these transitions get obsolete very quickly. So experience replay, apparently is a showstopper for most learning to communicate problems. This is a very recent result from Lowy, where they use these schedules, as I talked about before. What they do here is they have shown pretty much that, well, emerging a language is hard. That's one of the main objectives of the whole research on learning to communicate. is to see if two agents can actually learn to develop a language of their own to do some task, or even to learn a pre-existing language like English, for instance. And this is very difficult because in order for two agents to develop a language on their own, it means that since they're doing random exploration, they need sort of to coordinate, to make the same explorations at the same time. And this happens very rarely. So the current state of the art, as of 2 months ago actually, is that rather than doing self-play from the outset, what you do is you collect data from some expert system, and you do supervised learning with that training set on your agents. That's called the supervised learning phase. And then you follow this by a self-play. So you emerge your language from there, but you need to begin somewhere. The recommendation is not to begin training from scratch or from randomly initialized networks, because the thing will just never converge. And there are, these guys propose different types of schedules just to do that. I mean, this is the case where they do first self-play, and then they do supervised learning from some collected data set. They can alternate randomly as well. Here they introduce what they call parameter freezing, which what they do is basically they don't train the speaker, they only train the listener, and this also helps the listener adapt quicker to what the speaker has learned. And this one makes interrupted freezing of the parameters of the training of the speaker. This is just a bunch of a list of papers on agent modeling agents, deep reinforcement opponent network or drone. I think. Let me see my notes. Yeah, I think this approach just basically adds two neural networks to the agents. One is the agent's own neural network, and the other one is just trained to try to mimic what the other agents are doing. And they use this, again, to try to predict in advance the actions that the other agents would do. And yeah. And there are many ways to do this. You can try just to model the policies. You can try to model the Q networks of the opponent. So yeah. Yeah, maybe I want to skip this and move, in the interest of time, to the next. Yeah, this is fun part. So I couldn't resist to put a video here. So have you all read this paper, by the way? This is the Alpha Star paper. Who has not read it? OK, good. Then I'm going to show you the video because it's very fun. I guess you all know StarCraft, but for those of you who don't, I don't have volume. OK, we don't need to watch it all, but that's pretty much the video game. That's the challenge. Has anyone here played the StarCraft? No one has played the StarCraft. Yeah. No one has played the StarCraft. What's wrong with you guys? My goodness. OK, it's a video game, strategy game. You need just to defeat the enemy and command those troops, and they need to build houses and collect resources and so on. So this paper was published by DeMine last year, I think on Nature magazine, and basically they use reinforcement learning to solve this game. And this is a very interesting environment to solve because it takes place in real time, and it certainly requires a lot of long-term planning. So you need to define very long-term strategies in order to beat the opponent. And I wanted to summarize here what are the main techniques that DeepMind has actually used to create AlphaStar, which is the software that actually beats StarCraft to most players. So the first thing is that they do not use a discount factor. The discount factor is 1. Why? Because what they care about is about winning the game. There's no timer in this game. What matters is to win. It doesn't matter if it's now or if it takes you 2 years to win. What matters is just to win the match. So there is no need for a discount factor here. They use a deep LSTM, they need memory. So in StarCraft, it's a partially observable game. So you don't have access to the internal state of the game. You only have access to a small fraction of the map, everywhere you can see your own units. And the way they disambiguate this is by a very big LSTM network. I think I read they use that this network, this network has 140 million weights, so it's a pretty damn big network. They use this technique, which is called an autoregressive policy, and this idea I like a lot. So in a StarCraft, the action space is very large, okay? So at every time step, you as the player of the game have many options at your hands. You can move the mouse and put it anywhere on the screen, many pixels. You can click on a unit and move it to, again, anywhere on the screen. You can shoot. So the number of actions available to you as a player is counted in the millions. So how do you work with such vast action spaces? What they do is they introduce the concept of so-called structured actions. So even though the actions have so many degrees of freedom, what they do is they have identified, I think, a total of 15 or 20 main action categories. And then within each of these categories, those categories are things like moving a unit, or shooting an enemy, or moving the map. Okay, so those are the categories. And then within each of those categories, again, you have many degrees of freedom because you can click pretty much anywhere on the map. But first, you need to select the unit, which are not so many, and so on. So there's a structure, there's a hierarchy in the selection of these actions. So what they do is they introduce the concept of the autoregressive policy, which means that you have a stochastic policy for a given state that depends on your actions. But now this policy is conditioned on the actions you took in previous times steps. Okay? So the moment you choose as an action moving a unit, all of the other actions, like shooting an enemy, are completely out of option for you. So those other actions are blocked. So in this way, you can actually restrict a lot the options that each agent has on every time step. And it allows you to address very large action spaces. Another thing they did is that they initialize the agents. I mean, they use supervised learning for initializing the agents. I think this is sort of a trick. So if you remember the AlphaZero paper, which was famous some years ago, AlphaZero was really a tabula rasa technique, which meant that the software didn't know anything about Go when it began training, but this is not the case for AlphaStar. What DeepMind did is that they collected data from many human games, and they did supervised learning using this human collected data to train their agents. And then they evolved it from there. So that's why I was surprised that this paper was accepted by Nature magazine, because again, it's trained using human data for starters. Again, they also use a state representation that collects all of the previous observations and actions. So their state space, again, is very large. So that's how they disambiguate this problem with partial observability. Even if they don't have access to the whole map, to the whole state, they certainly keep the history at hand in order to take their decisions.
What rate do they take actions and observe?
I think for training, I don't know, I guess very fast because it's software, but I know that's when they play against the StarCraft champion, they had to introduce these restrictions so that they're
not taking
it cannot take every millisecond an action, because otherwise it would be unfair when playing a human. Yeah, but that's only for gaming. I guess for training, you don't really need that.
One thing in the last assumption, basically you can go every part of the map and memorize it.
Yeah, I guess you could do that, yeah. Was that a question, or?
No, I mean, if you can memorize all the map, then it's not.
Yeah, but memorizing the map in StarCraft, it means you have to explore it. So you have to move your units around the map. If you haven't played StarCraft, you won't know, but you need to. It takes time to explore the map. And if you do that, then I guess your opponent could attack you in the meantime. So yes, it's good to explore the map, but you also need to take care of other.
You can explore where your enemies are. So
Yes, yes.
probably that in the beginning.
Yes, but they move as well. So that information is only valid for so long. So there are two memory techniques in AlphaStar. One is, as I said, this very large state representation, and the other one is this huge LSTM. I don't know how much memory this has, but I guess a lot.
Might add, it's also a resource game.
resources to build troops. So if you just build explorers, they will, your opponent will run you over with military units and destroy your base. So it's heavy strategy. This is definitely not simple.
But it's a fixed scenario, right?
Sorry?
The scenarios are fixed.
Fix? What do you mean fix?
Like, when I start the match, the
Yeah.
scenario will always be the same.
I think they train this for several races, and I don't know about the scenario, but I guess each race has its own scenario. This I don't know. I don't know. You'll have to read the paper, but.
Even with all this assumption, I think this program couldn't be the future.
Yeah, that's a good point. To me, there are two reasons why this paper should not be in Nature magazine. The first one is that it's not tabula rasa, and the second one is that they claim that AlphaStar has reached grandmaster level. That means that it beats 99.98% of all humans, but that still means there's a couple of humans that beat AlphaStar. So it's not like the Deep Blue of StarCraft yet. So again, yeah, it's a remarkable achievement, but is it worth Nature magazine publication? I don't know.
It can actually beat 98.9.
Yes, because apparently you can play StarCraft Online. There's a league with thousands of people playing, and this software beats pretty much everybody there.
Did they also do self-play after this initial?
Yep. Next slide and last slide. Okay, and the other main innovation of AlphaStar is what they call the league. They introduced this concept of the league training. Basically, this means that this is to solve a problem. When you're doing self-play, you have a problem. You have a problem that you may chase cycles. So self-play means that you evolve your agent. The performance of your agent improves over time. But then you have a problem that even though agent version 2 beats agent versus 1, it turns out that agent versus 3 may lose against the first version. Okay, so these cycles occur very often when you do self-play. So the way they solve it is that they create what they call the league. So periodically, they freeze past versions of the agent. Okay, and what you do is when you train your main agents, those main agents play against all of those agents in the league, which is basically a collection of past versions of those agents. And they are trained, and the networks are updated not only after every single match, but based on averages from training against the whole network. And then it gets a bit more complicated, and this part is still not very clear to me. They have this other category of agents. They have what they call the main exploiters and the league exploiters. The league exploiters are agents that never play against the main agents. They only play against the agents of the league. And then they have these main exploiters whose job is to play against the main agents, but they're not as good. And they're just there with some original tactics that have been designed, I think hand-designed, in order to reveal vulnerabilities in the main agents. So this whole league training setup was put in place in order to make sure that these guys kept progressing and avoid these cycles. And that's it. I think that's all I have on reinforcement learning. So if any questions, please shoot.
In the learning to communicate, how well does this perform today, and how long does it take to train someone to recognize this?
I haven't built it myself, but from what I've read, it's very difficult to emerge a language. I mean, there are usually you have two objectives when you work with learning to communicate. The first objective is that both develop a language, okay, a language that doesn't exist, and the other one is to try to learn a language that already exists. This second target is easier, and I've run that in a very small scale in the lab, and this you can do. But emerging a language from scratch, from what I've read, is very hard. That's why the current state of the art suggests if you want to emerge a language, you need first to collect a training data set, do supervised learning on it, and then you can begin doing self-play. But do not attempt to do self-play from the outset, except if it's a very small vocabulary size, because it's very unlikely this will converge to anything.
It works.
In these small examples, yes. But if you want to do something more practical, well, we'll see. Okay, so if we're done, I think the next talk is from Berenice, who is going to explain to you what's coming up tomorrow in the Career Counselor. So if you want, sure.